So we're going to be going over project 4 for Dr. Ozbay's class, where we do part 1 of the project, which is simulating 2D flow over a stationary cylinder for 3 different conditions for inviscid flow, viscous laminar, and viscous turbulent. And we're going to be getting all of these different uh, contours and property tables. So let's get started. So we can drag and drop into Fluid. First thing we're going to do is our geometry, setting it to 2D and running. Alright, so we're going to be in the XY plane here. And first thing we're going to do is check our units, make sure it's in meters. We're going to sketch a circle at the origin and dimension it to 1 meter. And then I'm going to draw a rectangle, which is going to act as our like test section area. So draw it about from here to here, and then I'm going to make it symmetrical. So use the symmetry about the x-axis, and then I'm going to dimension out the walls. I'm going to make this 10 meters, and then I'm going to make this length about 30 meters. That way we have like a long area behind us, and that should be our proper test section. And then I'm just going to dimension this out. And that should be properly constrained. Now I'm going to concept surface from sketches, sketch 1, apply, and generate. And now we have our surface, and we can move on to the meshing. Alright, now that we are in our mesh software, we can begin the mesh process. So we're going to insert a method into our face, geometry, apply, and generate. See what that gives us. So not very good. I'm actually going to switch this over to triangles and regenerate, and then see what it gives us. Okay, it's a little bit better. So what we want is more triangles around the actual cylinder itself. So what we're going to do is add a, let me double check. We are going to add edge sizing, basically, to our cylinder, apply, and then we're going to use, let me double check, element size of 0.05. Let's see if that's going to give us that. Capture curvature, no. We're going to turn it to no. Hard behavior, and we can generate. And now we have a lot more triangles towards near our surface of our cylinder. Something else we can add to further refine it is inflation. Gonna select the face, apply, and then the boundary is going to be our cylinder. We are going to switch this to first layer thickness and switch this to 0.002, and then max layers to 25 and a growth rate of 1.5. And let's see what that gives us. Ooh, whoops, that's not right. Let me double check something. Okay, so what I did wrong was actually in my edge sizing, and I didn't choose the right element size. I chose 0.05, and it should be 0.005. That way we have a lot more of a fine mesh towards the inside, and it should look something more like this. That way we have a lot finer of a mesh near the edge of the cylinder, and it decreases further and further out as you go. The last thing we're going to do is adjust this to, let me see, we're going to adjust this to a smaller element size. We're going to switch this to, what did I set this to? 0. We could play around with the number, so 0.02. Let's see what that gives us. This might take a minute for it to load, given if you ask it to subdivide a lot of faces, so we'll see how this turns out in a second. Alright, I actually switched around a little bit of the numbers, and I switched this to 0.01 because I found my last value of 0.02 was a little too small, and it took a long time to mesh, and it was too fine, so all of this would have been like tiny, and we don't really care about this being too much, but we're really mostly concerned with the edge of the cylinder and then like sort of behind it. So this works for a mesh. It's a lot finer in the background, or in the back of the cylinder, and super fine around the edges. If we want to zoom in here, we can see this is what the edge looks like. And now we can start meshing, or we can start naming our boundaries. Obviously click this N. This is going to be our inlet. This is going to be the symmetry, these two walls. And this is going to be our outlet. And then this is going to be our wall. And now everything should be good. Let me just double check this by hitting update. And let's see, okay, the green check mark works. We can close this out and begin our processes. And double click on setup. Double precision. I set it to 2 solver processes because it's what my computer can handle. And we start our simulation. So let's look at the conditions. So the first one is going to be inviscid. Inviscid flow, you can take velocity as 5 meters per second. So let's see. All right. All right. Models we're going to go to because we need to switch this to an inviscid flow. Inviscid, and then let me see, there's nothing else in here that we need to change. Materials, fluid, air, gonna leave that for this run. Boundary conditions, inlet, we need to change. to 5 meters per second. Apply and close. Let's just make sure all of our boundaries are set properly. Outlet is set to outlet, symmetry, and our wall. Let's just make sure this isn't moving because this is a stationary cylinder. Okay. Reference values. Oh yeah, I'm going to change this. That way when we do our calculations, everything comes out correctly. So our velocity is 5 meters per second. Area 1, 1.2. All of these are going to be kept the same. Methods. Not going to change anything here. I'm going to initialize it. And then run calculations. For this example, I'm only going to do 100 iterations. For the actual one, probably be better to do more. That way you have more accurate data. And then from here, we can hit calculate. And it's going to run, show us the this graph, which isn't really needed. Alright, now it says calculation is complete. And we can start our analysis process. So let's see, get the velocity contours. That's the first thing he wants is the contours. So we can go here, contours, velocity, velocity magnitude, and there we go. We have stagnation points at the back. We have our max velocity at the very top, which checks out and is very close to the theory. Let me see. We can also show the actual streamlines in multiple different ways. We could do contour lines. It's not the best way. Save and display, close. We can go to path lines over here. Choose it by velocity, velocity magnitude of the interior surface body. Hit save and display. Let it run its thing. This might take a while because there might be a lot of contours based on the path. This will probably end up being around 400. That way we can see more of the actual streamlines and not just, you know, a bunch of arbitrary streamlines. So come back to this when it loads up. Alright, I switched a little bit of the parameters, that way it would load faster. I changed this to 400, that way we can see a little bit better of the path lines. What I'm gonna do is change the color map options. That way we just have white streamlines. What we can do, edit, delete a bunch of these, and then just switch this to white. Apply. And now we can just see white streamlines. And then in order to see them both on top of each other's, which is what I assume is what he wants from us, is this. We can change this to, I'll change it. And then we have the streamlines. You can see the small bit of vortex in the back of the stagnation point. We have streamlines that are sticking pretty close to the surface. So this looks just about right in terms of the matching the theory. So we can click out of this. The next thing that he wants is the pressure contours, which is pretty easy. Go back up here to contours, pressure, static pressure, makes sense. Highest static pressure at the front and the back, lowest static pressure at the top because your velocity is at the maximum. Dynamic pressure, let's see. Again, perfectly matches. You have a stagnation point, so the velocity is 0 at the front and the back. Um, pressure is dynamic pressure is the maximum at the top because the velocity is the maximum. And then the total pressure, this looks just about right. And the next thing he wants is the velocity distribution. Let's do that then by going to plots, XY plot, and then the velocity magnitude on the wall. And there you go. We have it along. I assume this is double because of the two sides of, so like the upper half and the lower half are about the same. They're just flipped a little bit. That should be good for part C. Plot the CP distribution on the surface of the cylinder. Let's see. Pressure, pressure coefficient, save and plot. It's the opposite, which makes sense as pressure and velocity act differently from each other. Um, the drag coefficient. Let's see. From that we can do we can go up to report definitions, new force report drag. And this is why I said it was important to set your reference values to the proper values, including changing the velocity, because it's calculating it from that and not from the actual simulation itself. Wall, compute, and we get a drag coefficient of about 0.01. It should be technically 0, but Ansys is going to give us a different value because I guess it's hard computing it um, and not going based off of theory, because based on theory there should be no drag in an inviscid flow because there's no frictional effect, there's no boundary layer, there's no slip condition, so there should be no drag. But Ansys is giving us a tiny little value anyways, which we can say it's neglectable and move on from there. Let's see. Compare the wake patterns. That's something we can do in our report, which is already included in my report. And for inviscid, or for the other two, we have to do a viscous laminar and viscous turbulent. So basically, if we go here, Reynolds number is very important for us. It's in determining whether a flow is viscous or turbulent or laminar. Basically, for laminar, what we can do first is switch this to a laminar flow. And then it is also very dependent on the velocity. So let me take out my calculator. So what we need is the density of the fluid, the velocity, and the length of our test section of our cylinder, which is 1 meter, obviously. So we're going to take 1.22. And if you forget, we can always go back up to our we go back up to our materials, double click on air, 1.225, and our viscosity. So for back to Reynolds number, go back to density times velocity. So we have 5 meters per second, and times 1.7894 times 10 to the negative 5. That is equal to 341,928, which is in the turbulent, or which is in the laminar region, so we don't have to change anything with our velocity, and we can pretty much just calculate from there. Go back and initialize it first, sorry. Initialize, and then run calculation and calculate. And now it's going to run. This might take a little second. And it is done. All right. Oop. You can see it's calculating all this stuff that we have open. Um, and we can, again, look at the contours. Contour 1. Ooh, we have a nice wake region here. Uh, due to the viscous effects. Go back to, we can look at our different pressures. Static pressure, total pressure, all that fun stuff. And then we can look at our XY plots. XY, XY. We can go to our pressure coefficient. You can see that's a little crazy. Velocity, save and plot. Should be 0 on the surface, or on the wall. Another quick theory check. This is correct along all parts of the cylinder because of the no-slip condition. So since it's a stationary cylinder, the wall isn't moving, there should be no velocity on the surface. And then we can again get the drag coefficient by going up to report definitions, new force report drag. We should have a bigger drag coefficient along the wall here. 1.22. There we go. Very high. Drag coefficient. And then lastly, in order for a viscous turbulent, we can just use a higher velocity in relation to the Reynolds number. So for me, I'm going to use, let's say, 50. Double check that it's in the turbulent region. Oops, sorry. Should use. Yeah, that is very much in the turbulent region for 50 meters per second. It's above it's 3 million Reynolds number. So it's definitely in the turbulent region. So what we can do is switch this to K epsilon, and then where is it? Switch this to we're going to do 50 meters per second, apply, and then close, and then go back to our reference values, switch this to 50, and now we can run. I'm going to initialize it again, and then I'm going to run and calculate. And then it should finish up in a few seconds. And now, okay, now we can go to our contours again. Velocity, more of a wake region here, more of a slimmed down wake region. Go to our pressure. Oops, pressure, static pressure. No static pressure in the back, more in the front. Dynamic pressure, same thing. total pressure looks good. And then our plots, velocity, again, nothing along the streamline, or nothing along the wall. We can look at pressure coefficient, seems to match. And then our drag report. Back to reference, or back to report definitions, and force drag compute 0.2459. All right, and that should be just about everything that he wants for the project. The last thing that he wanted was to compare the wake patterns and drag coefficient, which is something we can do in the report. Yeah, and that is the end of this tutorial.